Thank you. I actually want to make another clarification. There's since the original presenter that for this thing was Dr. Simon C., and he could not attend. So they asked me to stand in, and I guess I added a little bit on what to do, but all the technology presentation slides are coming from him. So in the end, there will be his email. So if any of you have his questions concerning that part, you could write him. Okay. So actually, I would never make such a pretty picture. Anyway, so this is how they developed the graphics cards since time immemorial, I guess. So originally, graphics was just an interface between computer memory and the screen. And then they started to turn the GPUs into actual processing units. So now we have a separate computer inside our computer. And it became more and more complicated. And then in second half of 2000s, they actually realized that many people, realized that actually many people in scientific community, and I guess in engineering community as well, started to use the potential that they see all the processing power from the graphics card. And they used really complicated techniques to get their data into the graphics card and then get it back using all the OpenGL. That is not supposed to do that, actually. So then the manufacturers realized that they could do that, turn that into something useful for everyone. And I guess in 2006 or 2007, NVIDIA introduced this CUDA technology, where you could turn your graphics unit processing into something you could process non-graphical data more easily. And since then, they developed more and more cards, actually started to produce cards that don't even produce any graphics output on its own, like some Tesla cards and some of the Fermi cards. And their current is the Kepler card, which is, I guess, a lot more powerful and quite less power consuming compared to other cards. And there's some future there as well, although actually no idea what the future is for their cards. Okay, now the library. Not the library, actually. So what we have in these graphics cards. Since it's a separate card, it's attached to PCIe interface, so it has its limitations. But inside that card, we have quite a lot of separate computer cores, a lot more than on general, usual, or any computer processing units. That's because the cores on graphics cards are a lot simpler. They don't do a lot of input-output stuff, for example, and they also lock together to work in groups, what they call in warps, I guess, in NVIDIA technology, and I think in OpenCL it's called something else, work group or something. So anyway, with the GPU cards, they become a lot more parallel, and then with proper algorithms, they can produce a lot more results than the CPUs. Okay, and yeah, I guess another explanation, the same thing. So on the CPU, you have a few cores, and they have cache, and then there's a connection to PCI bus, and the memory is also connected there. And in graphics cards, you have a lot more cores combined together, so they have also small amount of cache, and they can move the data between cards and then to the main memory and to the processor as well. So they're not that isolated. And then again, the same thing. Have a few cores on the CPU, but those cores are a lot more, how to say, have a lot more possibilities to do all these different calculations. And you have GPU accelerator cores, which are a lot simpler, but they work a lot faster and they work in groups. So how it's done. For each of the tasks, there is called a thread in terminology used in CUDA. Thread is one core doing sequence of commands. Those threads are associated in blocks that all of the blocks are doing exactly the same commands. It's just that each of them is using separate piece of data that it's supposed to process. And those blocks are merged into a grid. And that grid is actually covers all the data that needs to be processed, and each block is worked on its own part of the data. And that's how you access. There is this variables within the library that you can get for each of the threads, to let it know what part of the work it's supposed to do. And all the blocks have their own small memory that they all share. They're called shared memory, and then there is all general memory or device memory that all the blocks, all the threads have access to, but blocks don't have access to shared memory of another block. So there is this separation. So then you make your algorithm have to take that into account, because shared memory is really fast and the device memory is a lot slower. Okay. Okay, and now again to reiterate the same thing. So we have all these ways for each of the threads to identify where it's at the moment, and then all these blocks can be 1 and 2 3-dimensional indices, so that you can process data and can split your data in all the possible combinations and make it linear, make it 2-dimensional, make it 3-dimensional, and so on. Actually, not so on. 3-dimensional is the largest what's allowable, I guess, for devices at the moment. Now, how it's done. So each of the graphics units have separate of streaming microprocessors, and each of those microprocessors has 8 of processing units, and those units combine, each of them have several floating point calculation units and several units for things like for transcendental functions and other things. So things like floating point and simple things can be done with this single processor. So they can be done. So if you just do some simple calculation, it gets processed really, really fast and in parallel. And if for some reason some of the at some moment some task needs to calculate some transcendental function, then they call the SFU units, and then every other processors wait for that unit to free, and then so that's kind of serialized in this sense. But modern processors have more of these transcendental units, so that means that the whole thing is getting even faster, still keeping small in size. Okay, and now when you try and really do implement all this parallelism and properly, you can really get a lot of speed up depending on the how well you do your parallelization. For example, molecular dynamic things called NAMD actually was designed to be as parallelizable as possible, and it is actually works well, and this is done on a single machine. But because it's trying to be parallelizable for any different, well, actually it was originally designed to be parallelizable for a CPU cores, and then it's for distributed cores. So its parallelization, so its parallelization not as perfect as fine-tuned things like done for Ember, for example, another molecular dynamics unit processing. However, then we try and run it on several machines. That's where the NAMD parallelization thing actually helps, that it's really spreads out between very different machines and really helps. Okay, and then again, the biggest to date supercomputer is built actually of NVIDIA cards, GPUs. All right, now the programming part. So we have the libraries. Okay, all right. So how do you program GPUs? It's a bit complicated because all of them are quite different. So there has to be some layers. You have your libraries that already have been fine-tuned to run on GPUs, but present some high-level interface to your application. Or you can use that now emerging another OpenMP-like interface using called OpenACC, where you actually don't really care what kind of acceleration devices you have. It could be multi-core processors, or could be graphics units, and so on. And then there is also programming language interface that is a lot closer to the device, to GPU. And that, of course, will give you maximum flexibility, because you can really fine-tune things, but in that sense, you have to, in that case, you really have to know what you are doing. Okay, and this is an example of two things. So this is an example of a standard thing called SAXP. So it's an example of a vector operation. You take two arrays of values, multiply and sum. So it's one of the typical examples of parallel code. So in a standard C code, you get serial multiplication, run through all the values and calculate. And in parallel C code, that's an example of so-called kernel, that the task that each of the threads runs. So you calculate what value you need to work on for this particular thread, and calculate that value. And then, and the last line is actually you call these lines for all these blocks, and each blocks of size. In this case, 256 threads per block, and this many blocks, and then it splits all the tasks. The driver splits all the tasks and sends it all in the GPU and run like this. So you see, in the first sense, it's just it runs one by one, and in the second example, it runs all in parallel, or as many parallel tasks as the GPU supports, but and then it still runs the whole thing. Okay. Now the CUDA libraries. So you have your code that works with. You write your code, and then you submit it to a special compiler program called NVCC, which actually, so your code looks like a C code. It is a subset of C, and it creates special assembly code, and then that assembly code is actually not a real assembly for GPU, actual GPU, but it's kind of a virtual assembly code, so that it goes to another compiler, which actually compiles, makes a binary, produces machine code for a particular graphics card that you have, because they have different now, I mean, like maybe, sorry, different architectures, so the codes for them and optimization for different applications would be different. That's an example of this PTX. I mean, nice looking assembly code, but we're actually trying to move away from that. Okay, now another thing that you need to know about all this parallelization is that, again, that when you run things and you split your data in blocks, and you know that blocks can interact with each other, but you cannot really expect them to work in order. It can be arbitrary, it can be done in some ways that, for example, if some memory area that, for example, block 0 needs to access is busy at the moment, then it runs block 1, which has, whose memory is available, for example. So it's always done within GPU, and you don't really need to care about that. So it really works in this sense. Okay. And actually, one good thing about these NVIDIA cards is it really help with, really put a lot of effort in being helpful to program their cards. So they produce quite regularly new drivers for their cards, update their toolkits, and the toolkits are pretty complete with compilers and libraries and debuggers. And now recently they also have an integrated development environment too, so it's also very convenient, and a lot of examples, and there's a lot of support on the web as well. Okay, and now also with this compiler, they also produce a lot of libraries that are fine-tuned to run on GPUs, and actually now they have adapted for a library called BLAS, so the linear algebra library, and in the FFT library, and random numbers, and the sparse matrix libraries, and a lot more too. There's a profiler, and as I said, so it's getting more and more easy to program it and fine-tune it and debug it and everything. And they also have, well, with the libraries, you only program it, you could see what your device is, what it can do, because they have different generations of this, and you can actually adapt your programs to run on depending on what the device can do. And there's a lot of really explanations in the methodology of parallel programming, because it's still very heavily developing area, and especially then you have this kind of programming model. Then you split your data in groups, in blocks, and all the blocks have this memory, shared memory, and there's this device memory. So all of this is really kind of takes a lot of effort to understand and to realize and really make it work. But when you make it works just amazing. And anyway, and there is a lot of already prepared libraries for this, and they are being used as well. Okay, now one way, really easy way to start when you're still programming in C++, I guess. Start to use OpenACC. Now it's is being supported by many compilers, and I think PGI also makes a special fine-tuned compiler that creates GPU codes. But anyway, with hints like OpenACC, you can tell just like with OpenMP, you can tell that this is going to be a parallel process code. So try and split it and run it. And this is an example. Then there's a 2 level of iterations, and then there's update, and then this is how it's done. You tell your with the first pragma, you tell what area, what matrices are going to be needs to be put in GPU, and then the second pragma tells that this is going to be a parallel process, and then it's all done automatically during compilation time. It's still kind of very convenient, but then again, it's not too, how to say it, not too deep in, you can't really fine-tune all the things. Okay, so, and in many cases you don't really have to, because there's a lot of all these libraries that have done that already. So if your tasks are more or less straightforward, like linear algebra, and matrix algebra, and all the numerical methods that have been adapted, and all that, there are already existing libraries. Some of them are free, some of them are not, and still they are there. Yeah, and there's a comparison task that you see that properly fine-tuned CUDA BLAS runs 6 times as fast as Intel MLKey library for that similar tasks. And MLKey is a library developed by Intel to work to do again the same things as BLAS does on multi-core processors, but GPU is much faster than even than 32-core processor, I guess. Okay, and there is a support for sparse matrices, algebra, if anyone works with that. They actually started to do it, I guess, only about 2 releases ago, so I guess still being developed. And a very nice library to work with pseudo-random numbers, because again, that actually was one of the problems before, because pseudo-random number generation is actually quite serial task, if you know, because the next value depends on the previous values in some form. So to run it in parallel took some effort to actually make it work properly. But now they have a special library, and it's really becoming very easy to do. Okay. Now they also so far the libraries that come from NVIDIA with the cards are don't support this C, C++, and Fortran, and all the other languages will have to work through that layer of them. And then But I guess they now, since recently they have moved to support this LLVM compiler. Actually, it's now works a lot more, and I guess it gets more unified in this sense. So to add new languages to it is going to be much easier. But that's still going to the same problem that you still have to understand what's happening inside the GPU and how to program it properly. To help with that, we work with Python library already, because it's already quite mature in this sense, and we have libraries to already do all these tasks, and we can work through those libraries. And yes, can work with those libraries as well. For example, so there is a library called Copperhead. Actually, it's not exactly a library. It is a library, but it's also part of effort to parallelize Python. It has different backends. It can compile for GPUs, or also supports OpenMP. So you could just choose which one to use, or actually you could let it choose automatically. It would check that if you have GPU, it will run on GPU. So in Python, it's as simple as to add a decorator. You could see include some stuff from Copperhead library, and then just decorate the function that you want to run in parallel with the CU decorator. And it actually implements on a low level all these functions like map and reduce and all other things. So it actually, in a way, it has another compiler inside it, so it takes whatever formula you give it and then converts it into proper GPU code or OpenMP code or whatever you have. And it seamlessly works with NumPy in this sense. So you could see it's pretty simple compared to what you would do in the same SAXP example on pure Python, or change it to work with Copperhead Python. And this is very convenient and also fine-tuned, and it's inside the library. And there is another library called PyCUDA, which is a lot closer, or actually allows you to get a lot closer to GPU if you want to. For example, an example on the left is that you actually provide your kernel code, and this is a source model. Then you give the code in the C language that compiler from CUDA understands, and then you do all the other stuff. So, and then you compile that code, and you can run it. Or you could use one of the libraries that it already has. So, for example, there is a method called element-wise, which does exactly the same thing as example here. Well, actually, element-wise runs on CUDA the function that you define and then produces results. And then, so in a way, this is a simpler way to do the same thing as here. And in this sense, this is a very simple function. You can, the performance that you get is very similar, but I guess in some other more complicated ways, it's better to use what already has been fine-tuned before. And another thing is with pre-made libraries like this, on the right, like the PyCUDA element-wise versus PyCUDA when you compile your own code, is that when you compile your own code, you also have to take care of how you're going to run it. So you have to define what your block size is, how many threads per block, how many blocks per grid, and that actually might influence performance. So you have to fine-tune it, and it actually does depend on what graphics card you have. Or you could use the code on the right, but actually finds the optimal values for the block size and grid size, and just runs it for you. So when we try and compare the results with this, so I've run actually this test for all these codes that were listed before on my workstation that had a Quadra 600 NVIDIA Quadra graphics card. So it's not a dedicated card, but still, you could see that pure Python takes per million elements takes 5 seconds, and Copperhead takes a lot faster, it's about 200 times faster. And the PyCUDA actually both variants give about the same timing, so I just left one with the straightforward code on the left. It is a bit slower than the Copperhead version, but I guess that's because it was just CUDA version and not fine-tuned one like the Copperhead library has. So with this, you would probably go again and say that with this, as when you are moving your code from existing C library, for example, like I'm doing here, I'm actually pretty novice in Python, but I've done a lot of programming using CUDA. So actually now I'm moving it into CUDA Python because before you could see that I had my CUDA code, then on top of it there was some C++ library wrapper code. That on top of that there is another wrapper code from C++ to Python, and then there's Python. So with these things, PyCUDA and Copperhead, it's a lot easier to remove just the other two layers, and you get straight to the code. And another thing is that coding like this, then you have your source code as a string, and then compile it, again, just in time. Compiling it allows you to really fine-tune it, and in fact, actually, you could also create templates and do all this wonderful meta-programming kind of techniques with this, and it's going to be really, really helpful in this sense. So with all this, right, so that's what they do. So they have a lot of libraries, and there is a lot of applications, and a lot of research is done in this, and research used a lot of results. And in fact, I've done all my calculations, all my reconstructions that I do with the virus structures on a cluster that I've assembled actually here. That has, I have 10 nodes, and each node has 4 to 6 GPU cards. So I have a cluster that has 40 GPU cards, and its performance is comparable to a much larger cluster with CPUs, and it consumes a lot less power and takes up a lot less space, actually. It's just one mountain rack. All right, and oh yeah, and I guess that shows that once more that how much effort NVIDIA actually puts into support of this CUDA technology. So they produce all these libraries, they support all these new things, introduce new things. That's really works out very well. And the good thing, actually, as I said before, you could start running it already on your workstation because there is a large chance that you have a GPU card, NVIDIA GPU card there already. And that's what we're working. Yeah, well, okay. And anyway, yeah, so we can see the development again. So we had a lot more, had a transition with a highly parallel processors to distributed processors, and now we have kind of moved a little bit back again. We have dedicated processors for computation, like GPUs, and have normal processors for managing anything else. And I want to thank you. And again, most part of this talk was done by Dr. Simon C. And I've just helped a little bit too. So thank you.
It's regarding the PyCUDA code. I noticed that you passed a whole chunk of the code, which is equal to Python, right?
Yeah.
It looks quite strange. I mean, it's not very beautiful. I mean, it's very important for Python programmers to have this kind of feeling. It makes the language very easy to use. And
yeah, well. Yes, all right. Actually, that's what I tried to show that, but I guess wasn't clear enough. Yes, I guess that the main attractive feature of Python is simplicity in many cases, and that's why it's getting so popular compared to other languages. And actually, I guess that the Copperhead library is trying to do just that, trying to add very little overhead on top of what you're already writing. In fact, you could just include the libraries add that decorator, and that's that. And you don't need to do anything else, and the rest will be taken by the library. However, again, like with any, you can get as complicated as you want with this. If you, especially as I was saying, if you, for example, transferring some code that you have written before, this is the way to go. Then you just put the code in there, compile it as it's needed, and run it. Or you could just try and see that actually for some pieces of your code you have already good implementations in the library, you switch to that. And again, or if you don't need to do anything else, or actually if you know what your code is supposed to do, you could go back and do simple things with Copperhead. It's just that the good thing about it, and actually that's what I like about Python, is that there are all these possibilities. You don't really need to stick with some particular way of doing things.
Okay, thank you very much. We are running a little bit short on time. Thanks again.